Hello and welcome back to this course. In this lecture, we're going to talk about the back propagation algorithm that is used to train a neural network. And basically, this is how a neural network learns. It learns using the back propagation algorithm, which we'll be discussing in this lecture. So let's move ahead. Consider this data set, this very small data set that you have that consists of 3 samples, and each sample has 2 features. Now what we want to do is we want to teach this network to map this input to this particular output. So when the input is 0.5 and negative 0.5, we want our network to output 0.9 and 0.1. And when our input is 0.3 and 0.4, we want our network to output 0.9 and 0.9. And finally, when we have 0.7 and 0.9, we want it to output 0.1 and 0.1. Now you can also consider these as binary values. So 0.9 just means 1 and 0.1 just means 0. Okay, but here I'm going to work with decimal values and not binary values for a purpose you're going to understand later on. But usually in practical applications, you do have binary values such as a 1 here and a 0 here. Okay, so your y or your targets here are 1 0 1 1 0 0. So we want to map this input data to this output data. Now in this lecture we're going to consider one sample, and then the same exact thing happens for the other sample. So let's take this sample as input, and we wish to map these 2 values or this sample to this particular output. Okay, so when we have 0.5 and negative 0.5, we want to teach the network using the back propagation algorithm to output 0.9 and 0.1. So this is the neural network that we're going to work with. If you'd like the reference, then I've taken it from a textbook called Neural Networks, a Classroom Approach. So D1 and D2 here are your expected outputs. And remember, they're 0.9 and 0.1. So here we have 2 input features and 2 neurons in the output layer. Okay? So since we have 2 features at the input, that means the number of neurons in the input layer should be 2. And now the number of neurons in the hidden layer, I'm just going to set them as 2. And the number of neurons in the output layer, since we also have 2 outputs, that means the number of neurons at the output layer should also be 2 in this case. Okay, so we wish to map the first sample to the first feature of the first sample to 0.9 and the second feature of the first sample to 0.1. Now the first thing we need to do is initialize our weights. So these connections here are the weights. Realize that each neuron is connected to all other neurons. So this is connected to this, and this neuron is connected to this neuron and this. Okay? So the first feature that we were working with is 0.5, and the second feature that we're working with is negative 0.5. These are the 2 features for the first sample. Now we're going to just initialize our weights randomly, but of course, we'll be talking about weight initialization techniques. There are some different techniques for weight initialization that we'll be speaking about in a separate lecture. But here, we're just going to consider that we randomly initialize the weights. Okay, so these are just some random numbers that we set, because we have to start somewhere. Of course, we can't start with 0s or 1s, and why I'll also talk about that in the weight initialization section, why we can't start with 0s or 1s, or why we can't even set them all to the same value. So why can't we initialize all weights to have the same value? I'll be talking about that in the weight initialization section. For now, these are our weights, and we've randomly initialized them. So let's proceed. Here we are also going to consider the bias terms. So remember, we spoke about the bias in the perceptron lecture. So each neuron has a bias associated with it that helps the neuron fire if the weights and inputs are not sufficient. Okay, if needed, of course. Okay, so we're going to start by moving forward. Let's take this part right here. This neuron in the first neuron in the hidden layer. So this receives input from the first neuron and the second neuron at the input layer. Okay, so the net input value comes from the two neurons in the input layer. So what we're going to do is multiply each input with the weight and sum them up, as we learned in the perceptron lecture. Okay, so the net value is the total input coming to the neuron. Okay, so we have x1 times 0.1 plus x2 times negative 0.2, and finally plus our bias. Now remember, the bias is always 1. The value of the feature is 1. So basically 1 times 0.01 is just going to be 0.01. Okay, so this is the equation that you have. And now if you add them up, you'll get 0.16, which is the net value for the first neuron in the hidden layer. Now let's proceed to the second neuron in the hidden layer. So again, the same thing. Net input value equals to x1 times 0.3 plus x2 times 0.55 plus your bias, and you'll get a value of negative 0.145. So we finished calculating our net input value, and now what we need to do is the activation. So we're going to take the output here for the second neuron and the first neuron, and we're going to run them through an activation function. Okay, so this neuron is divided into two parts. The first part is the net input value that it receives, okay, which is Z here, Z2 for the second one and Z1 for the first one. So this is the first part of the neuron, which is Z, and the second part is the activation of Z. Okay, so in this particular lecture, we're going to work with the sigmoid activation function, which scales the input value to the range 0 to 1. Okay, so sorry, it scales the net input value to a range from 0 to 1. Okay, so this is using the sigmoid activation function. This is the equation, if you recall from the activation functions lecture. This is the equation of the sigmoid activation function. Okay, so what we're going to do in this case, plug in our Z here and get the activated output. So X here is the net input value, which is Z, as we saw before. And lambda here is just a scaling factor. For simplicity, we're just going to consider this as 1. So let's go ahead and plug in Z1 and Z2 in our activation function. So when we plug in Z1, if we remember Z1 is 0.16. So when you plug it here in this equation, you're going to get 0.5399. And when you plug in the value of Z2, which is negative 0.145, so negative with negative becomes positive, and therefore the result of this equation is 0.4638. Realize that both of them are scaled to a value between 0 and 1. Okay, so this is the output of the activation function. Now let's continue with the neurons in the output layer. So we've finished up until here, and now we're going to proceed to these output neurons. Okay, so this is what we have right here. Now the hidden neurons output become the input to the next neuron. So the outputs that we get here become input to this neuron in the output layer. So remember that we get 0.5399 for this neuron and 0.4638 for this neuron. So we're going to use these inputs, okay, and these inputs are going to be multiplied with their weights. So 0.5399 times 0.37 plus 0.4638 times 0.9, and we're going to add the bias, and we get an output of 0.9271. Similarly, we do the exact same thing for the second neuron in the output layer. So the inputs times the weight plus the input times the weight plus the bias, and we get a value of 0.0955. So the outputs of each layer become the input to the next layer. That's essentially what's happening here. So we're done calculating the net input value for the output neurons. Now, again, we're going to run them through an activation function. So we just plug in 0.9271 here in this sigmoid function, and we get 0.7164. And similarly, we plug in the value that we got for the second output neuron, and we get 0.5238. So this is the output layer, and these are the values that we get after the activation function. Now we're going to calculate the loss based on these values. So here we finished talking about the forward propagation. Now we're going to start back propagation. So the back propagation is a method to train the neural network. And when we say train, we mean that we want to adjust the weights of the neurons for the purpose of reducing the loss or the output error. So just a small recap about the back propagation. The underlying concept of how it works is using gradient descent. Remember, we're taking the negative of the slope and using it for updating the weights. Okay, so our objective right now is to find this slope right here, the derivative of the error with respect to the weights.